Good evening, students, and welcome to today's session. Okay, Aditya. So I will be discussing some of the doubts which are pending from last time, and then other doubts which I have received also. I will also be discussing some revision questions of my own while I'm going through the doubts and discussing them. You can try those questions yourself. So we will start with a mechanics question today, which I'm putting up on the board. You can try out this question, and in the meantime, as you're attempting this, I will be going through your doubts and discussing some selected questions from among the doubts also. Yes, Ganesh, I have received that one. I will be discussing that also. That Boolean algebra, I think, which you have asked, right? I was just going through that. Okay, so let's go through this. Right. So right. So let's start with this particular example. So fairly standard kind of situation in system of particles mechanics kind of thing, but with some additional concepts we'll discuss here. Okay, so this is a wedge kind of thing, which is lying on a smooth horizontal surface, also against a wall initially. So this is a smooth surface. This is a rigid wall, fixed wall. Okay. Now this wedge has like this hemispherical cavity kind of thing in it. So this is a smooth hemispherical surface, okay, of radius r. Now what we are doing at t equal to 0 is a small spherical body. Oh, sorry, this is not smooth. My mistake. You would have seen the version of the smooth one before, but it's a modified question where this is a rough hemispherical surface, whereas the ground below is that one is smooth. Okay. So now what we do is at t equal to 0, a small spherical body, solid sphere kind of, okay, such that its radius is very small compared to this one. So a small spherical, solid spherical body is released gently from the corner point A, and we have to assume that it rolls down without slipping. So this point is like this. Okay. So at time t equal to 0, a small solid sphere of mass m and radius r. Okay. Assume r is very small compared to capital R. Okay. And m by m ratio is 1 by 1 by 6. Okay. So the mass of the sphere is 1/6 the mass of the wedge. Okay. So it is released gently from the position A as shown. Okay. Assume it rolls down the hemispherical surface without slipping. Okay. So next thing what we have to do is we have to calculate a number of things here. So if capital M is 24 kgs, G is equal to 10 meters per second square, and R is equal to 20 meters. Oh, sorry, 20 centimeters. Meters. First of all, calculate the net impulse applied by the wall, by that rigid wall on the wedge after releasing the sphere. Then you have to calculate the maximum height to which the sphere reaches after crossing B for the first time. You have to also calculate the speed of the wedge at the instant when it just loses contact with the wall. And we have to find out the maximum speed of the wedge after the system starts moving. What is the overall maximum speed of the wedge going to be? Okay, so start working on this question, and I will also be doing some of the questions that you have sent as doubts, some of the questions pending from last time also, and some of the questions I've received in between. I'll be discussing those after going through this question. Okay, now I'll just discuss a few points about this. If you're confident about the question, just continue with your solving. I'll just explain a few points that you have to understand on how to approach this question first. Okay. So what is happening is that, see, initially when the sphere is coming down towards the lowest point B on the hemisphere, okay, at that point of time, if you look at the force picture, the interactive force between the sphere and the wedge, there'll be contact force like this, okay, and there will be frictional force like this on the sphere and equal and opposite like this on the wedge, okay. And so the sphere will have what we can call a velocity relative to the wedge. I mean, initially the wedge is at rest, so the sphere will have a velocity v like this and an angular velocity omega like this, okay. Because what will happen is that this wall will absorb whatever impulse. So there's like a reaction force or a normal reaction which the wall is applying. So R is the force by the wall on the wedge. Okay. So this is happening till what? This is happening till this comes to the lowest point B for the first time. Now the moment it comes to the lowest point, okay, now what happens is that the interactive normal reaction is like this, okay. And you'll also realize that, you know, at that particular moment there won't be any friction acting because there's no tangential force on the center of mass, okay. But a moment later, of course, there will be friction acting. So that is when this reaction force becomes zero. Just at that moment the reaction force becomes zero, okay. And by now, let's say the sphere, its center or its translational velocity has become v naught and its rotational velocity has become omega naught. So v naught is equal to r omega naught, and you can see that this thing, half mv naught square plus half I omega naught square is equal to mgh, where h is more or less equal to r because small r is negligible compared to capital R. So you can make use of all this, okay. And we'll come to how to calculate the impulse and all this. This is at that point B. Now when it crosses the point B, then again the situation becomes very interesting. Once it crosses the point B, now you will see that the wedge starts moving, okay. So now the momentum starts to transfer again in a different way. So when the sphere is now somewhere here, you can see that the normal contact force, it has a horizontal component on the wedge, and by now the wedge has lost contact with the wall. So there's in fact even a gap now. By now the wedge has got some displacement like this, okay. And of course friction continues to act. So now friction will act like this, it will decelerate, you know, and on this it will act like this. But anyway, so now what is happening is that we can say that with respect to the wedge, this one has a linear velocity v relative and an angular velocity omega, whereas the wedge itself has some horizontal velocity v prime, let's say, okay. And this picture now continues, so you know we can visualize frame after frame what is happening. So you know this is the starting. Now this is happening at some, you know, so this is going from frame 1 to frame 2 to frame 3. So next in our set of frames, let's say it comes to a situation where this one has reached the highest point on the other side after crossing the point B. When this has reached the highest point, what will happen at this point of time is that its v relative will become 0, okay. Its v relative will be 0 and its omega will be 0, whereas this will be moving with some, say, v1 at that point of time, okay. And then it will roll back down, okay. So next thing in our frame is that now the sphere is somewhere here, So it has relative velocity like this, angular speed like this, and this has some v prime again, okay, or whatever, v double prime or whatever. And next comes to this situation where so at this lowest position, so at this point of time, it has some v relative like this and some omega like this, whereas this has some, okay, say v triple prime or whatever, something like this. Okay, and then it starts again rolling up. So this kind of situation now happens. Whatever, some velocity. So this is the general progression of events. Okay, now you have to see that what all we can conserve, when we can conserve, etc. Okay, so one conservation equation I have already written for you. Okay, so in fact, I'll just remove this from here for the moment, so that. So try to recognize what is happening to the system between each of the frames. Okay, so between frame 1 and 2, because the wedge is stationary, so what is happening? The sphere is just rolling down a fixed hemispherical surface. Okay, so because it's rolling down, there is conservation of energy, but there's no conservation of momentum or angular momentum or anything like that. So 1 to 2, the wedge is fixed. Okay, but the kinetic energy plus gravitational potential energy for the sphere, this remains conserved. Okay. Then 2 onwards, what is happening? Now the impulse from the wall is 0, or this lost contact. Okay, so now for the wedge plus sphere as a system, what is happening? Horizontal momentum is conserved. Okay, and of course, kinetic energy plus gravitational potential energy is conserved. But by kinetic energy, we now mean kinetic energy for the block plus the sphere, or for the wedge plus the sphere. Okay, so this is all for the wedge plus sphere as a system. Okay. And all the time it is rolling friction which is acting, so there is no slipping at the point of contact. So there is no energy dissipated by the rolling friction. Okay, so now make use of this sort of guidelines over here, and of course use the values given that capital M is 6 times small m equal to 24 kilograms, which I have given to you, and capital R is 20 centimeters, G is 10 meters per second square. Okay, so try to properly select what concepts you will use for which part of the question. Okay, so go through this once, and I'll take you through the questions again, question once more, and then we'll discuss the solution. Yeah, I mean, best is if you work out the numerical values. I will work them out for you. Okay. So let's look at the first part of the question. Okay. So we have to calculate the net impulse that the wall is applying, okay, after the sphere is released. So you can understand that the wall is applying force between picture 1 and picture 2. That is, while the sphere is coming back from the point A to the point B for the first time. When it's rolling down from A to B for the first time, till it reaches the point B, there is impulse from the wall. The moment it crosses the point B, force from the wall tends to become zero. So to calculate the impulse by the wall, net impulse by the wall, so you can see that from this instant till this instant, okay, the wall is applying some kind of force. So if this is some t equal to 0 and this is some t1, r dt integrated from 0 to t1, this is equal to the change in horizontal momentum of the system. Okay, if you take x as your horizontal direction and y, so this is equal to nothing but this small m v naught. So this is the impulse. Okay, this is the impulse applied by the wall. So for this, we just have to calculate v naught. Okay, and we just discussed that from picture 1 to picture 2, the sphere rolls down. So okay, so here this will become, okay, because it's rolling. So omega naught is equal to v naught by r, because remember this thing is stationary. This is at rest. So it's rolling on a stationary surface still. Okay, so like this. So this will be the impulse. The mass is 4 kg. No, beta? Have you taken the mass to be 6 kgs by mistake? Small m is capital M by 6, no? So it is 4 kg. Okay, good. Okay, so that's the easiest part of this. Okay. Now see, the next thing we have to do is we have to calculate this thing, the net, the maximum height to which the sphere reaches after crossing the point B for the first time. Okay, and actually the third part you can see it's actually this part is very easy. At speed of, not sorry, I didn't mean the speed of the wedge. I mean the speed of the sphere. Obviously the, okay, so this is actually from the first part only. This is the same thing as the first part, that v naught only root 10 by 7 gr is the speed of the linear speed of the sphere at the instant when the wedge loses contact with, obviously the wedge will start from rest, but okay, so at the instant when the wedge loses contact with the wall, just make that correction in the question. So that is also answered in the first part only. Okay, now let's come to the second part. Okay, so this also tells us that the third part, v of the sphere is equal to this v naught only root 10 by 7 gr at the instant when the wedge is going to lose contact with the wall. So now we have to go from this image where this is having V naught and this is having omega naught, and this one is at rest, to a situation where now this happens. The ball has already lost contact with the wedge. The wedge is in a state of motion, and the sphere has reached this highest point. So it is at rest with respect to this thing. Okay. Just magnify this a little. It's difficult to. So the relative velocity of the sphere is 0, and the angular velocity of the sphere is 0. But this is moving at some, let's say, v naught at that point of time. So sorry, not v naught. V naught we already used here. So let's say this is moving at v1. So between this picture and this picture, what is happening? This is the maximum height to which this will climb. Between this picture and this picture, for the system being the wedge plus the block, horizontal momentum is conserved. So mv naught should be equal to m plus capital M v1. So v1 will become v naught by 7, or 1 by 7 root 10 by 7 gr. Okay. And now to find h, we'll do energy conservation. So along with this, so this is the second part of the question, to find that height, okay, when it reaches this point. So we'll do energy conservation now. So half mv naught square plus half I omega square should be equal to half m plus m v1 square. Okay. Now interestingly, you can see that this quantity is actually equal to mgr from the first part. You can see that this quantity. So we can directly equate mgr is equal to half m plus 6m v1 square. Sorry, plus mgh. Okay. And see here we have this relation that half m1 plus 2 by 5 v naught square was mgr. This was from first part. And we've got from here that, okay, so when we equate this now, this is 7 by 10 mv naught square is equal to half of 7m into v1 square. Now v1 we can substitute from this equation. Substitute the value of v1 from here. Okay, so v1 is becoming v naught by 7. Okay. So this will become how much now? 1 by 14, is it? You're replacing capital M with 6 times small m here. And you're replacing v1 with this. So this is your energy conservation equation. Okay, this was your conservation of momentum. Horizontal momentum, actually, not conservation of momentum, but conservation of horizontal momentum. So anyhow, let's see what this gives us. Just check my calculation once, but this is what I'm getting. Ten by seven, no? Oh, sorry. Yeah, yeah. My mistake. Yes, yes. B naught has to be substituted with 10 by 7. Square root of 10 by 7 G. So this will become how much now? 88 by 14 into 7. So this is 88 by 98, is it? I mean, there are several ways of doing this calculation actually. You can also do it this way, that to keep this MGR the same, minus 7m into V naught square is equal to MGH. So now you substitute this over here. 7 by 2 into 10 by 7 GR MGH. Yeah, so you're saying we'll get the C. Okay, so the values are clear, I hope. You can see it's almost going up to the top. 44 by 49 is only slightly less than 1. But yes, it doesn't go all the way to the top of the hemisphere because the kinetic energy of the system is not becoming zero. No? It's becoming. Okay, now next part of the question is the most interesting thing. As you see, third part we've already calculated. The speed of the sphere when it loses contact, that we've got. Now we have to find the maximum speed of the wedge once the system has started moving. What is the maximum speed that the wedge develops? Okay, so for that, I encourage you to go through this series of diagrams again and try to identify that at what point of time the wedge will have maximum speed. Okay, just go through this series of events here and try to identify at which point of time the wedge will have maximum speed. No, Aditya, that is not correct. Think once more. See what is happening after that now. See what's happening in this series of events here. No, Amitav, that's not correct, unfortunately. Anyone else, in which diagram the wedge will have maximum speed? Yes, Somadip, that's correct. Aditya, that's correct now. Because you can see that in this diagram, in the sixth one, sorry, I'll just take you back. In the sixth one, see, from 2 onwards, horizontal momentum of the system is conserved. So the horizontal momentum of the wedge will be maximum in the positive direction when the sphere has maximum horizontal velocity in the negative direction. So that's what's happening here. The horizontal momentum of the sphere has a maximum negative value. Okay. So correspondingly, the horizontal momentum of the wedge will have maximum positive value. Okay. So basically, all the way now, from here onwards, you can see the impulse picture. Now also, you can see that the normal reaction that this is applying on this, it's all the time pushing, but now it starts pulling back. So up to here, the wedge is pushed along positive x direction. Here also the same. But now the wedge's speed starts decreasing. Okay, from here, the wedge's horizontal momentum is decreasing. Here, the wedge's horizontal momentum is increasing, right up to this point, up to the sixth diagram. Okay. So as the sphere rolls back from the highest point back to the point B, the wedge continues to accelerate. And the second time the sphere crosses the point B, that's when the sphere starts to decelerate. Okay. So that's the important thing to understand here. Okay. From the time the sphere crosses B for the first time until it crosses B for the second time, the wedge accelerates along positive x direction. Okay. Then after the sphere crosses, after the sphere crosses B for the second time, the wedge starts to decelerate. Okay. So that is the important thing to understand. This point of time, nothing is happening. Acceleration of the wedge is 0. But now after it has crossed B for the first time, and this is on the way up. So at this point of time, the wedge is having a positive acceleration. then it reaches that highest point and starts coming down, then also this is having a positive acceleration. But then as it crosses the point B, now it starts rolling up this. This is the point of time when it starts decelerating. So in between, when it reaches the lowest point for the second time, that is when the speed of the wedge is maximum. So now what we will do simply to understand that is we'll compare the first diagram with the sixth diagram in my earlier series of diagrams. So in the sixth diagram, this speed, let's take as V1, this is the maximum speed of the wedge. And let's take this in ground frame only to be V2 and this to be omega 2. So V relative is actually V1 plus. Okay. And now let's compare this and this. Oh, sorry, we cannot compare this and this because momentum will not be conserved. Only energy will be conserved. So we'll have to compare when it was at the lowest point for the first time. That time this had a V naught and an omega naught. We compare this diagram. I think this was the third diagram or whatever. Compare this with this. Just about losing contact at this time. Okay, so compare these two situations to find out this maximum speed. So here again you have to be very careful about the rolling motion condition and the constraint for no slipping. Here the wedge is at rest, so it's very easy as we had solved earlier. But here the wedge is moving with V1 towards the positive x direction. The sphere's ground frame velocity is, let's say, V2. So the relative velocity of the sphere with respect to the wedge, that relative velocity is V1 plus V2 in magnitude. Okay. So please try and calculate this properly. Okay. Okay, so has anybody solved the equation to find out this V1? I'm starting to solve the equation, so please compare if you're doing the same. Okay, So between 1 and 6, we will do for the system, that is the wedge plus the sphere, we'll do conservation of horizontal momentum. Okay. So small m v naught will become capital M v1 minus small m v2. So that's our first equation. So you can substitute this as 6 times small m. So this will become v naught is equal to 6 v1 minus v2. This is our equation 1. Okay, and we will do energy conservation. Mechanical energy. So this becomes our second equation. Now in this we can substitute this term. This term can be just substituted as mgr only. Okay. And here, so, and of course here this will be substituted as 6m. So first of all, that will give us a modification, that but we have to be careful about the omega. Okay, it's not going to be v2 by r. Give us this for the moment. Okay, now we will have to understand the no slipping constraint. Okay. The best way to understand the no slipping constraint is just get into the frame of the wedge. Okay. So in the wedge's frame, it's very easy to understand. With respect to the wedge, this one has a relative velocity of v1 plus v2, and it has an angular velocity of omega, and the point of contact should be at rest. Okay. So in the wedge's frame, velocity of the point of contact should be 0. Okay. So v relative should be equal to r omega 2. So this equation becomes actually that v1 plus v2, sorry, not capital R, small r. So v1 plus v2 is equal to small r omega 2. This becomes our no slipping constraint. So this is an important little concept here. Just go through it carefully and understand the application of relative motion, how I made use of that. Very critical to solving the question correctly. So now see how we will incorporate all this here. Okay, so since we are solving for V1, okay, it's a better idea to eliminate V2 first. Okay, but instead of V2 now we'll use relative velocity. So this equation we can write as V0 is equal to 6V1 minus of, now see V1 plus V2 was V relative, which is R omega, I mean small r omega. So we can write this as V2 is equal to R omega 2 minus V1. Okay. So now we have this relation that V0 is equal to 7V1 minus R omega 2. Since in this equation we are substituting this. Okay. So now we have R omega in terms of V0 and V1. Okay. We have V2 this is from equation 1. So we substitute both of these in this equation. So this equation becomes mgr is equal to half m 6v1 plus v0 whole square plus half 2 by 5 m. Now r omega we will substitute as this thing, v0 minus 7v1 whole square. Okay, plus 3mv1 square. So we now have an equation like this, that so we can cancel m also on both sides. Okay. So what you do here is you take v1 as the unknown variable x and solve this as a quadratic equation. And that v1 will be the maximum speed of the wedge. So you'll get v1 in terms of v0, and remember to substitute v0 as square root of 10 by 7 gr finally. Okay, So it's still a bit of a job solving this quadratic equation. So I'm not getting into the full solution because I want to discuss more questions. Okay. But yeah, in JE, if you get a question like this numerically, one is to you can get a question conceptually where you have options where the different quantities which are conserved, or at which point of time the velocity of the wedge becomes maximum, and all these things you have to clarify. Matrix match question or more than one option question. So without calculation, it's just about the solving part, about the conceptual part. The other is if you get a solving based question, the values will be such that the quadratic equation cancels out easily. I've taken the ratio of the masses 1:6, so probably things are not cancelling that easily. Maybe if I'd taken 1:7 or 1:14 or something like that, these equations would have been easier to handle numerically, that is. But the method of solving is still the same. So this question I wanted to discuss. Okay. So anyhow, I will send you the solution of this and the question, so you can go through that later. Now, next, I want to discuss one of the questions sent by Aditya. I'll try to discuss few of the questions sent by each one of you. Ganesh has sent a question. Aditya has sent some questions last time which are pending. Devash, there are some questions of yours pending, and of course, Samyak, some questions of yours are pending. So I will try to discuss questions from each one of your doubts. Okay, but one of the questions I have selected next is from Aditya's set because. I mean, I'm trying to go with the merit of the question so that we can discuss few concepts from that. So let's discuss about this question quickly. Actually, also, one of the questions we had done last time where the answer was not matching, Samik, that question of yours of the two springs, there was actually an error. I will discuss that question with you. There was an error in the constraint relation. So I think the answer is correct according to what you were telling me. So anyhow, just go through this question next. We will discuss this. Okay, so let's go through the working of this question. Yeah, Ganesh, I'll verify. Okay. Okay, so the main thing here is you have to look at the impulse picture. Okay, when the sphere comes in contact with the surface, what is happening, because the sphere initially before contact, the sphere had a velocity which had this type of components. Its velocity had a positive x component and a negative y component. So as a result of that, it has a tendency to slip like this at this point. So not only there will be some normal impulse, we can say n delta t or whatever, but there will also be some frictional impulse f delta t. Okay, so this is the collision impulse. So this is in fact that kind of case where the surface is rough, so there won't be conservation of tangential momentum. Even the tangential momentum will change. So these are the collision impulses. Okay, so as a result of that, now let's say after the impact, okay, what is happening is that the momentum is having a changed value of that x and y component. Okay, so let us say the impact velocity was v naught, and the impact was happening at an angle theta. So here this angle was theta. So you can see that before impact, we had ux was v naught cos theta and uy was minus v naught sine theta. Okay, so after impact, suppose the velocity is becoming something like this. Now let us say after impact, there is some vx and vy. So this velocity is becoming vxi cap plus vyj cap. Okay. Now, first of all, the question is saying that we may assume that f is equal to mu n during the impact. Okay. So that means the frictional impulse will in fact be equal to mu times the normal impulse. So we can make use of this. Okay, so just a moment. Okay, now what we want to do is we want to find the condition on theta so that the range is maximum after impact. So after impact, what is happening? The range will be like this. If this component of velocity is vx and this component of velocity is vy after the impact, so this range that we get, this range will be equal to vx into 2 times vy by g. Okay. Now we can see from here that if we apply the impulse momentum picture, n delta t is equal to vy plus uy into m. Okay. So vy is equal to v naught sine theta. Sorry, it is equal to n delta t by m minus v naught sine theta. So we can say that vy is some y component of impulse minus v naught sine theta. And similarly, we can also see that along the x-axis, okay, So remember, I'm taking x-axis like this and y-axis like this. We have the impulse along the x-axis is minus f delta t, and that is equal to m vx minus ux. So vx will become ux minus f delta t by m. So vx will become v naught cos theta minus mu times n delta t by m. So this is my first equation. This is my second equation. So you can see that the range is like this. It is v naught cos theta minus, now let's write this jy by m as some quantity. Let's write it as a delta v, because it has, so it is mu delta v into 2 times delta v minus v naught sine theta, like this. So this range is a function of theta like this. You can see it's a function of theta. So we can find the maxima of that function by putting the derivative with respect to theta as 0. Understood now? So from here on, this is what you have to do over here. You have to just open out this function. It's a function involving, linear terms in sine theta, cos theta, and a product term of sine theta, cos theta. And then you have to differentiate it and put its derivative equal to 0. So Ganesh, is this the method you have used to solve this? Achha, you use the AMGM concept while solving it, okay? On the last example. So yeah, you have maximized the range by using AMGM. Okay. Now see, one one thing you can do further to make the equation simpler for you now. Since it's asking for a condition on theta in terms of mu now, you can just arbitrarily assume that this is an elastic collision. So if it's an elastic collision, the separation velocity should be equal to the approach velocity. Okay, so that will just give you a much simpler way of solving this. Okay, so for the special case, of this elastic collision, perfectly elastic collision, what will happen is that your Vy will be equal to Uy, will be equal to V naught sine theta. Okay, so then your delta y is very easy to calculate. Now your delta V over here, this expression is just going to become 2 V naught sine theta. So your Vy will become V naught sine theta, and your Vx will just become V naught cos theta minus mu into this thing, mu into delta y, sorry, delta v. So that is 2 v naught sine theta. So this is an easier thing now. So the range now, vx into 2 vy by g, this is easier to handle now, okay, compared to this expression above. But anyhow, it will give you the same kind of result. Acha, is given in the question that it's perfectly elastic. Okay. So then you use this condition that it is perfectly elastic. So then yeah, obviously you can use the AMGM method in this. Okay, so this is an easy function too. Yeah, I think otherwise if you take the general case, then it's also a function of the coefficient of restitution. So it also depends on that ratio of delta V and V naught. So in this case, that ratio of delta V and V naught is 2. So you'll get a specific value of the theta, okay, which Ganesh you have calculated. So I'll just put up that value. Tan inverse of 1 plus 1 by 2 mu. So range is maxima will occur for theta equal to tan inverse of 1 plus 1, 1 upon 1 plus 2 mu. So this is what you should be getting. Okay. Now, before I move on to the next doubt, yes, I want to just clarify that question we were doing last time. So we had this massless pulley, and there were two springs which were identical, connected by massless threads. And we wanted to find the distance. I mean, we wanted to find the pulling force. So this was a spring of constant K, and this was another spring of constant K. So the massless thread, massless pulley. And this distance here was H. So we have to find what force with which we should pull that point so that there is, it reaches the ground over here. So I got the constraint relation wrong. Okay, in fact, what you people were suggesting was correct for the constraint relation. Later, when I worked it out on pen and paper, I realized. Okay, so now let us say this pulley has come down here, and this point has come here. So in this diagram, if this length was L1, and let's say this is where the spring is connected, so this length was L2. This diagram, this has become L2 plus X2. This has become L1 plus X1. Then first of all, the displacement of the point P, oh sorry, this is not the displacement of the point P. This is the displacement of the point P. So the displacement of the point P will in fact be X1 plus X2. Because what will happen that on this side the thread is decreasing by X2. So on this side the thread length has to increase by X2. So in the pulley's frame, the displacement of the point P with respect to the pulley will be equal to X2 downwards. Okay, not 2x2 downwards, it's just X2 downwards. And the displacement of the pulley itself is X1 downwards. sorry, 2x2. Plus x1. Yeah, this is the thing. Yeah, okay. So now from this you can see that the displacement of the point P will become 2x1 plus x2 downwards. Yeah, that's okay, Samik. I just want to clarify for everybody discussing this in a classroom environment. Okay. And then of course there's a constraint relation that whatever force you are applying here is this tension, and this tension is equal to the force in the spring. So kx2 is equal to T. Okay, and 2T is equal to kx1. Okay. So you can see that x1 will become equal to 2x2. So this is from the free body diagram of the pulley. This one, okay, and this one is obviously this one. The tension in the thread is equal to kx2. So this is equation 1, this is equation 2, and obviously we know that F is equal to T is equal to kx2. So from here we have the displacement of the point P is equal to 5 times x2. So this height, if we want the displacement to be h, this has to be 5x2, which will become, now x2 you can see from here is F by K. So F should become equal to KH by 5. So I got the constraint relation wrong. I got it as 3x1 plus x2. It is in fact 2x1 plus x2. Okay, so this is this question. Okay, now I'm just moving on to another doubt next. So next I'm picking up a doubt from Bhumik. Okay, now this is again an important type of question, so we'll discuss this. Okay, so we'll discuss about this question, and there's another similar question that I want to discuss, but one which has induced charge. Okay, Ganesh. Okay, so what you do, the first thing over here is that you understand the distribution of charge now. So what is happening is that we have given the small sphere which is inside the shell and of radius small r. Okay, So small charge q is distributed on a hollow sphere. And we'll have to assume that the solid sphere around that is neutral. It hasn't been given any charge from before. So that means how the induced charge will be there. There will be some uniformly distributed positive charge here. So that charge will be plus q. Okay. Now that will induce a uniformly distributed negative charge on this inner surface. So Bhumik, I hope you're understanding this induction. So that will be minus q. Okay. And because the sphere is now neutral, the solid sphere is neutral. So there will be plus q that comes outside, and that plus q will also be uniformly distributed. Why it will be uniformly distributed? Because this charge is not influenced by the charge inside. The electric fields are cancelling each other. No? So this is also uniform distribution. It is a uniform sigma on the outer surface of plus q upon 4 pi r2 square. This is also a uniform distribution on the inner surface. Okay, even though they are not concentric. Okay, and this is uniformly distributed on the sphere. On the inner sphere. So, Bhumik, is the charge distribution clear to you? Okay. So now see, once you got the charge distribution, now you visualize this as a system of capacitors. So there is a uniform, I mean, radially symmetric electric field like this over here. That is storing some energy. And then there is a radially symmetric electric field with respect to the center of the solid sphere. With respect to the geometrical center, there is this electric field. So this electric field, okay, so it's like, you know, this inner region is the capacitor. So the total energy of the system will be the energy of the inner electric field. So that is like a spherical capacitor. Okay, so half q square by c, where that c will be one by r minus 1 by r1. Okay, so this will become q square by 8 pi epsilon naught 1 by r minus 1 by r1 plus the energy in the outer region. So the outer region's electric field, that will be like a capacitor, like a single spherical conductor. So the outer one is a single spherical conductor. So its capacitance is 4 pi epsilon naught r2. Okay, and its energy is q square upon 2c. So this term will become q square upon 8 pi epsilon naught r2. So now the sum of these two things. So you can see that it is going to be k q square by 2 1 by r minus 1 by r1 from here and plus 1 by r2 from here. Okay, so it should be A should be the correct answer. So this is the easiest way of visualizing and solving the problem. Divide it into two system of capacitors. You know, one, this region here is acting like a spherical capacitor, which has this kind of energy. Bhumik, is it clear? And the other is this region. This is like this. This is like a single sphere which has been given charge q. So it, you know, formula of capacitance. Okay, so that region has the energy which is given by this. And now just add these two energies, that is giving the net energy. Okay. Now I'll discuss more doubts, but also want to discuss a question of induced charge, something which is having the concept of induced charge in more detail with you. Okay. So this one is a spherical metallic conductor with center at O or center at C and radius equal to A. Okay. Now it has a spherical cavity. This is the cavity at with the center at O and radius B. Okay, such that CO, this distance is small c. So this distance here, this is small c, whereas this radius is A and this radius is B. Okay. So you can see C is greater than B, A is greater than all of this. Okay. Now the system is neutral, and what we are doing is we are placing two charged particles. One charged particle is placed outside and one charged particle is placed inside. So charged particles plus Q1 and plus Q2 are placed as shown, such that the distance from C to Q1, or let's say so the distance from C to P1 is 3a, and the distance from O to P2 is equal to B by 2. Okay. So what we have to do now is we have to calculate. Okay, this conductor was uncharged. Okay. So first of all, find the net charge induced on the inner surface of the cavity, okay, and the outer surface of the sphere. That's one thing. And next, what we have to calculate here is the potential of the metallic conductor. What will be the electric potential of the metallic conductor? Okay, so just try out this question very calmly. You have to use the concept of superposition over here. Very carefully, you have to understand how the superposition of events will result in the net distribution of charge. No, Aditya, check your answers again. Anybody else got the answer for the net charge on each of the surfaces? So, Somadev, is it in terms of Q1 or Q2? The charge inside is plus Q2 and the charge outside is plus Q1. No? Yes, that's correct. Correct, that's correct. Okay, so let's discuss about the charge distribution and then the potentials. So what I'll do is from the beginning, we'll understand it as a okay. So what happens here is that if we have a sphere with a cavity and the cavity is asymmetrical, okay, and we place a charged particle asymmetrically inside the cavity, we place charge plus Q2 over here, okay, and obviously this is the center of the solid sphere, this was the center of the cavity, let's say, like this, and all that. So what will happen is this will induce an asymmetric negative charge like this over here. But it will induce symmetric positive charge outside. So if I take this as my event A, so the result of event A is that the inner surface has asymmetric charge, okay, but net charge of minus Q2, and outer surface has symmetric distribution of plus Q2. So the outer surface has sigma of plus Q2 upon 4 pi E square. Okay. Now also what will happen as a result of this is that obviously we talk in terms of electric field lines. You know that there will be the sort of asymmetric field lines inside. So somewhat like this. Or originating, oh sorry, originating from the positive charge, not from the origin. Yeah, now talking about the electric field. We have field lines which are like this. Asymmetric kind of field inside, but radially symmetric field outside. Okay. So now we can see that, and in this region, of course, electric field is zero inside the conductor. So the potential of the metal because of this event is equal to the potential at the surface, okay, that is obviously outer surface, is equal to the potential at the center, which will become K times Q2 divided by E, because this radius is E, okay, or plus Q2 upon 4 pi epsilon naught E. So why this is happening is because at any point the potential is basically the potential due to the sigma on the outer surface plus the potential due to the sigma on the inner surface plus the potential due to the charge particle plus Q2. Now what is happening is that the combination of these two is becoming zero, and this term alone is equal to plus KQ2 divided by E. So that is another thing that we have to understand, that the sigma on the inner surface plus the charge particle itself together, they cancel the electric field. So together they don't create any potential at any point. Yeah, Somadhi, it's a solid conductor but with a cavity, na? Yeah, so Bhumik, the sigma on the outer is symmetric, na? Because see, the electric field at the surface has to be radial. Why? Because it's a conducting surface, na? So it cannot have a tangential component. Or moreover, you can see that the charge that comes on the outer surface, that plus Q2 charge, it is not influenced by the charge inside because their electric fields are cancelling each other. So it distributes like a free charge. right? Is it clear, Bhumit? जो plus q2 बार वाले surface पे आ रहा है ना, it is not getting influenced by the charges inside because they are shielding each other ना. So that distributes just like if you take a solid sphere without any cavity and all that and give it charge plus q2, how it will distribute symmetrically. So now this system of the charge outside, it is not influenced by the cavity and the particle inside it because they are cancelling each other. So this entire outer region is shielded from the electric field of the particle because of the induced negative charge. So this charge distributes like a free charge. So that's why it will be symmetric. That's why it will create a potential like this. And that's why the potential of any point in the metal, including the center of the metal sphere, will be like this. Okay. So this is a complete description of the first event where we are getting the sigmas also. We can see they are asymmetric, symmetric like this. And we know the potentials. And not only we know the potential of the metal, but we also know the individual contribution from each of the charges. Okay. Now we will do the similar thing for the second event and then we will superimpose. So to understand the second, in fact, what we'll start with is we'll start the analysis with something like this, that suppose we didn't even have a hollow conductor or a conductor with a cavity. Suppose we just had a solid metallic conductor. Okay. And we just placed a charge plus q1, okay, at some distance from its center. That distance we have taken as 3a and the radius of this one itself is a. So what would happen as a result of this? There would be some distribution induced charge minus over here, okay, but positive on the other side. This kind of distribution of charge would have occurred. Okay. So that the electric field lines would now be like this. Emanate from here and so, like, highly subjective kind of situation, but this kind of electric field lines would be there. So now the thing is, even if I have a sphere with a cavity now, and what this would do is that the electric field in the region inside would be 0. Okay. And in this case, what this would do is this would create a sigma on the outer surface, which is asymmetric. Okay. And net charge is 0 on the outer surface. Okay. But the potential of the metal will become constant, or rather uniform at every point. So at any point on the metallic conductor, the potential is going to be uniform. Okay. So whether I take a point here or here or here, wherever inside the metal, the potential is the same as the potential at this, which is the same as the potential at just inside the surface. So here, this is easy to calculate. Potential at the center, you can see, is, K into summation on Q on the outer surface divided by the radius plus K Q1 divided by the distance, which is 3a. Now this thing, because this net charge is 0, no? So this is going to be 0. So it is going to be plus K Q1 divided by 3a. So the potential of the center is equal to the potential of the metal in this case. Okay. So the potential of the metallic object only is plus kq1 divided by 3a as a result of this distribution of charge. Every point has the same potential inside the conductor. Okay. Now we can compare this situation with the situation where there's actually a cavity and all that. Okay. So you'll see the cavity makes no difference at all. So now this is my event B as far as that system was concerned. Okay. That I have the sphere, solid metallic sphere with the cavity. Okay. So this is my event B. and I placed this charge particle somewhere here, plus sorry, q1, okay, which is at a distance of 3a from this. So what this will do, this will do the same thing. It will not have any effect on the inner surface of the cavity, because the entire region inside the metal, it is shielded from that charge. So anything inside the metal doesn't feel the effect of the charge, because the charge induced on the outer surface is cancelling its effect. Field in this region is 0. So in this case, even electric field in this region will be 0, because I'm not placing any charge inside. So there's no induced charge on the inner surface. So because of event B, what is happening? The sigma on the inner surface is 0. There is no charge on the inner surface of the cavity at all. Okay. Sigma on the outer surface, on the other hand, is asymmetric. Okay. Such that the net charge is 0. So this is the same as this, same result. So this system will have the same effect as far as potential is concerned also. Okay. So you can see that the potential of the metal will be plus 3kq1, sorry, plus kq1 by 3r or 3a, whatever. So again, if you want to technically understand how this is happening, at any arbitrary point like this, okay, the potential is equal to the potential due to the charge plus q1 plus the potential due to the sigma on the outer surface. Okay, so these two are giving me how much? Because this has to be the same as the potential at the center. Yeah, so now we have to superimpose the two events. So the potential will also become the sum of this potential and that potential. Okay. So now when we superimpose events A and B, so we'll see that there is a very strange kind of distribution on the surface. There might be a bit of negative charge here, but predominantly it will be positive charge. And much more dominance of positive charge. Something like this. Okay. So sigma on the outer surface is asymmetric, because it is like the superposition of a symmetric and asymmetric. But net charge is plus Q2. Okay. Because there was Q2 symmetrically from event A plus 0 asymmetrically from event B. Okay. So this was plus Q2 due to event A plus 0 due to event B. Okay. But this was symmetric. This was highly asymmetric. So their combination becomes asymmetric. Okay. Whereas on the inner surface, we will see that there is just that event A's situation. Okay. Sigma on the inner surface will also be asymmetric. Okay. But the net charge will be minus Q2. So this will be minus Q2 from event A, asymmetric, plus 0 again from event B, and no sigma, no induction. So it's just that exclusive one. Okay. So now you can see that the potential at any point is going to be the potential due to event A plus the potential due to event B. Or you can also write it as the potential due to the sigma on the outer surface plus the potential due to the sigma on the inner surface plus the potential due to the particle Q2 plus the potential due to the particle Q1. Now this outer surface one also we can break into two sigmas. We can write it as V due to sigma on the outer surface Q2 symmetrically distributed plus the sigma on the outer surface zero charge asymmetrically distributed. Okay. So this is what we are getting from event A. This was getting what we are getting from event B plus, okay, which is minus Q2 asymmetrically distributed from event A, nothing from event B. Okay. Yes. So now you can see that the combination of this term and so this term is basically okay. Then the resultant of the next thing, the resultant of this term and this term together give you 0. Okay, and the resultant of this term and this term together, they give you that value of this. So that's why it is ultimately okay. So it is 1 by 4 pi epsilon naught this is the potential of the metal. Okay. So this is one question that covers everything about induced charge and potential due to induced charge. And obviously in these kind of cases, you can see the electric fields are highly asymmetric. Okay. So you cannot really do any calculation of electric field other than the fact that inside the sphere, the electric field will be 0. I mean, inside the metallic part of the sphere, okay, the electric field will be 0. So the electric field lines will look very, very asymmetrical. They will be something like this. And of course, inside also there will be those kind of electric field lines. Okay, so this is a very extreme example of the application of induced charge principle and superposition principle along with that. It covers all the different type of logics that have to be used in these type of questions. Okay, so people, hope this is clear. Now I'll just put up another question that I want to discuss from among the doubts. Okay, so let's go through this question and discuss this quickly. So for example, here, what we have to do is basically make a truth table. So you can see right now what is happening. A and B are both open switches, so they are 0. So what is happening to the output? Let's say this is C is the voltage across this, So when both of these are open, what about the potential of this point? Okay, the potential of this point, let's say this point is P. So VP is 0 right now. So you can see that the transistor is unbiased, because the base emitter junction, there's no biasing. So it is unbiased. Okay. So there is no current through this. Okay. So IC will be 0. So if IC is 0, you can see the potential of this point will be plus 5 volts. And the potential of this point is 0. So our V output is plus 5. So it's high. Okay. So the value of C is 1, or the resultant of A and B is 1. Is this clear, Ganesh? When both the switches are open, you can see this thing, no? The transistor is in an unbiased state, so there is no collector current. So no collector current means, basically, this 5 volt, how it is connected, it is the positive terminal of this 5 volt battery and the negative terminal is grounded. So it's same as connected here. So there's no current coming from this battery. So this point's potential is plus 5, whereas this point's potential is 0. So the output voltage is plus 5 or high. So C should be 1. Okay. Now next, let's see what happens when I close one of these switches. So let's say what I'm doing there is I'm closing this switch, whereas this is open. So A is 1, B is 0. Okay. So the moment that is happening, the potential of this point is becoming greater than 0. Okay, because there will be some current flowing through like this. So there, let's say some current I prime flowing like this. Okay. So the base emitter junction is forward biased, because you can see that diagram is a little unclear, but it's this type of. Okay. So this is a PN. Is an NPN transistor. Okay. And the collector, so you can see base emitter junction is forward biased. Okay. And you can see the voltage of the point C will be, nearly 5 volts. The voltage of this point will be this. So this is going to be collector base junction is going to be reverse biased. Okay. So there will be a strong collector current going through like this. So IC will be a large value current. Okay. So now to understand the potential across this, again you have to basically understand this. So this point is the same as ground potential. So this output voltage will typically become something like this. It will become 5 volts minus the collector current into whatever internal resistance of that battery. So it will tend to become a low this thing. So this will tend to become 0. Yeah, so that's the thing, Ganesh, which is a little bit tricky here, that how we interpret this thing, because there are no resistors. Now, ideally, there should have been another resistor connected here. Then this would have been a little easier to understand. Where the collector point is connected now, at the collector junction, there should have been another resistor like this, and then the battery should have been connected. Okay, so then it would have been easy to understand that this point's voltage is the output voltage. Okay, then it would have been easy to understand that the output voltage would have been this point, not that point. Okay, but in the absence of that resistor shown, we have to actually do this. We have to. Okay, so in the case of collector current being there now, this would have been just 5 volt minus IC to capital R, which would have become a low voltage in comparison. So anyway, so now you can see the same will happen for this also. So it is basically inversion of AND. Okay, so it is AND gate inverted, which is this. Okay, so hope this is clear. Particularly Ganesh, since this was a question we have asked, hope this is clear now. Answer is also correct. Okay, very good. So little bit ambiguity there, but you have to interpret it that way. Okay, so people will conclude here today because I have another lecture coming up, and I think you people also have a lecture coming up. But I have not got to discuss quite a few doubts which I wanted to actually, especially some doubts from Devansh, and also some more doubts pending, I think, from Samik from before. Anyway, so we will pick up the doubts in the next lecture, and again I will continue to do some questions of this type also. In the meantime, hope you people are working out questions from the revision test, revision question bank that also Gyaneshwar sir had sent to you earlier, I think, the physics, chemistry, maths revision banks. You can do questions from that if you finished all your other sources, or if you require any particular questions in any topics, you can let me know. I will also send you questions. Okay, so that's it for today, people. Wish you all the best.